Our universe is a strange and wonderful place. It's full of mysteries that keep astronomers and physicists up at night. One of the biggest puzzles is the flatness problem. We've measured the universe to be remarkably flat. This flatness is unexpected. It suggests a delicate balance of energy density in the early universe. But why should the universe be so finely tuned? This question keeps cosmologists on their toes. It hints at something profound about the nature of the cosmos. Perhaps we're missing a fundamental piece of the puzzle. Maybe our understanding of the Big Bang needs some tweaking. Or could there be something else entirely at play? Something we haven't even begun to imagine. To understand the flatness problem, we need to talk about energy density, a fundamental concept in cosmology. This is the amount of energy packed into a given volume of space, and it plays a crucial role in shaping the universe. In Einstein's theory of general relativity, energy density isn't just some abstract concept. It's a key player in the cosmic dance. It directly affects the shape of spacetime itself, determining how it bends and curves. High energy density curves spacetime, like a bowling ball on a trampoline, creating a noticeable dip. This curvature dictates how objects move through the universe, influencing their paths and orbits. A low energy density leads to a flatter spacetime with minimal curvature. Think of a bowling ball on a very stiff trampoline. The curvature is minimal, almost negligible. The surprising thing is, observations suggest our universe is incredibly flat, much flatter than we might expect. This flatness implies a specific energy density, one that's perfectly balanced between extreme curvature and no curvature at all, a delicate equilibrium that shapes our cosmos. Here's where things get really interesting. According to the Friedmann equations, which describe the evolution of the universe, a perfectly flat universe should also be a static universe. That is, it shouldn't be expanding or contracting. It should just be existing. Now, we know for a fact that our universe is expanding. We see galaxies moving away from us, and the further away they are, the faster they're receding. This expansion is a cornerstone of the Big Bang theory. So, how can we reconcile a flat universe with an expanding one? This discrepancy is a major aspect of the flatness problem. It suggests that our understanding of the early universe is incomplete. Section 4. The intriguing possibility of a closed universe. Here's another twist in the tale. The concept of a closed universe is both fascinating and perplexing. Even a slightly positive energy density, just a smidgen above zero, should lead to a closed universe. This means that the overall shape of the universe could be curved back onto itself. Imagine a universe shaped like a sphere. This spherical shape implies that space is finite but unbounded. In this scenario, if you travel far enough in one direction, you'd eventually end up back where you started. It's like living on the surface of a planet where you can keep going and eventually return to your starting point. Now, our observations suggest a flat universe, but they aren't perfect. The data we have is incredibly precise, yet it still leaves room for interpretation. There's always a margin of error. This margin, though small, could be significant in the grand scheme of things. What if, just what if, the energy density is slightly positive and our instruments aren't sensitive enough to detect it? This slight miscalculation could mean a lot. This possibility opens up some mind-boggling scenarios. It challenges our understanding of the cosmos and pushes the boundaries of our imagination. It means the universe could be vastly larger than we currently observe. The observable universe might just be a small fraction of the whole. Imagine a universe so immense that our observable patch is just a tiny, flat region within a much grander, curved structure. This grand structure could hold secrets and wonders beyond our current comprehension. Section 5. Beyond the observable, a vast and unknown cosmos. The idea that we might only be glimpsing a tiny fraction of the entire universe is both humbling and exhilarating. It suggests that what we know is just a small piece of a much larger puzzle, a puzzle that spans across unimaginable distances and timescales. It speaks to the vastness and mystery of the cosmos, a realm so expansive that it challenges our very understanding of existence. If the universe is indeed closed and much larger than we can see, it raises a whole host of new questions. Questions that compel us to rethink our place in the grand scheme of things. What lies beyond our observable horizon? Is there an edge, or does it go on infinitely? Are there other types of matter and energy out there, influencing the overall curvature of spacetime? Dark matter and dark energy, for instance, remain some of the most intriguing mysteries in modern astrophysics. Could there be other universes, each with its own set of physical laws and properties? The concept of a multiverse opens up endless possibilities and challenges our understanding of reality. These questions push the boundaries of our current understanding. They drive scientific inquiry and inspire new theories and experiments. They urge us to look beyond the familiar and embrace the unknown, to seek answers in the vast, uncharted territories of space. The flatness problem, far from being a mere cosmological curiosity, becomes a gateway to exploring the most fundamental questions about the nature of reality itself. It invites us to ponder the very fabric of the universe and our place within it.